All right, so what we have here is we have a summation from n is 1 to infinity of n plus 1, that's raised to the n power, divided by 4 to the n power. And they want to know, for the directions are for each series, what is the appropriate test to determine convergence? Well, one of the things that you need to observe here is both numerator and denominator being raised to the n. That's a giveaway that if you raise both of these to the 1 over n power, which is the requirement for the root test, and then evaluate the limit of that. We did this last week. So you evaluate the limit as n approaches infinity of the root of the series. What you end up with here is n plus 1 over 4. And then after evaluating this limit, if the result of the limit is less than 1, that tells you that this series converges. If the value of this limit is greater than 1 or infinity, that tells you, oh, and by the way, if it's less than 1, it converges absolutely, but we'll talk about that later. And then if it's greater than 1 or infinity, that tells you that this series diverges. And if this is equal to 1, well, that tells you that this test is inconclusive and you have to go a different direction. Well, I hope you see that if you put in infinity there, you get an incredibly large number. No limit exists there. Get an incredibly large number, which tells you, as I said earlier, that this would diverge. This would be a diverging, This series would diverge. All right, so that one wasn't too difficult at all. I think we'll have time for one more, possibly. I think we have time for one more. Let's look at another problem here. All right, so we've got a problem. This says same directions. For this series, what is the appropriate test to use to determine convergence? All right, so we got this problem. We're summing n is equal to 1 to infinity of 2 to the n power times n to the third over n factorial. Anytime you see that n factorial, again, that's almost a dead giveaway, similar to this problem where you see both numerator denominator raised to the n. That's going to be the root test where you raise both top and bottom to the 1 over n power, and you simplify it, and you can take the limit very, very easily oftentimes. That's a dead giveaway. You're using the root test. Here, when you see n factorial, that's sort of a giveaway that you're going to use a ratio test. You're going to use a ratio test, and again, that ratio test was where you evaluate the limit. N goes to infinity of a to the n plus 1 over a to the n, and absolute value of that. And what we said before, if the result of this is less than 1, you're looking at something that converges absolutely. You're looking at something greater than 1, you're looking at something that diverges. And if you get the limit equal to 1, that means that this test is inconclusive. I'm talking about, last couple problems I've tried to show you that there are a lot of tests that you're going to be confronted with. When you're in this subject, there are a lot of tests that you'll have at your disposal. And if you're able to easily look at a particular series and then come to a conclusion, hey, that's a factorial problem, so I'll need to use a ratio test there. Or if both top and bottom are raised to the n power, you need to observe those things to narrow down the tests that you are using. Because if you go in a direction where you end up wasting time, I guess I want to avoid that. So that's why I'm spending time showing you what should jump out at you for each of these individual problems. All right, so let's finish this power series here. All right, so what we got, again, we got the ratio test. So let's take the limit as n approaches infinity, and let's substitute n plus 1 here and here. All right, so we got 2 to the n plus 1. That's going to be multiplied by n plus 1 raised to the third power, and this is divided by n plus 1 factorial. Well, now that's a to the n plus 1, so now this test says divide that by a to the n. All right, so that's just the original series, 2 to the n times n to the third over n factorial. All right, and don't forget that that is all absolute value. All right, so let's evaluate this limit. So what we end up with is a limit as n approaches infinity of, you can expand this exponent here. We did that earlier. So that's 2 times 2 to the n power. And that's going to be multiplied by n plus 1 raised to the third power. Let's divide that by n factorial. All right, n factorial. Last week we showed you what factorial meant. So another way to write n plus 1 factorial is n plus 1 times n factorial. We talked about that last week a little bit. So now that's going to be multiplied by the reciprocal of this fraction right here. So we get n factorial up top divided by 2 to the n times n cubed. And as I said before in the problem we did earlier this evening, you're looking for cancellation. Hopefully you see there's cancellation here and here, and you've also got cancellation of the n factorial. All right, so now it's just as simple as evaluating this limit. So we got the limit as n approaches infinity of the result of this. All right, so what you have is you have, let's pull out the 2. You can pull out all constants with a limit. So you pull out this 2, and now what you end up with is you end up with n. Oh, actually, there's more cancellation. I didn't even notice that. I'm sorry. You've got cancellation here. N plus 1, that cancels with n plus 1 cubed, and you end up with squared. All right, so sorry about that. So what you got is n plus 1 squared over n cubed. All right, so now what you want to do is you want to evaluate this limit. All right, so what you have is you have 2 times the limit as n approaches infinity, and you can expand this out. You end up with, this simplifies to n plus 1 times n plus 1, and that is over n cubed. All right, so what you have is you have n squared plus 2n plus 1. That's being divided by n cubed. All right, so now it's a lot easier to evaluate this limit. So you get 2 times the limit as n approaches infinity. You get n squared over n cubed. Some of you might see what this limit is right away, okay, but I'm just showing all the work, plus 2 over 2n over n cubed plus 1 over n cubed. All right, let's just take it one more step. You end up with 2, and you evaluate the limit as n approaches infinity of, that's 1 over n plus 2 over n squared plus 1 over n cubed. Now it's very, very easy to evaluate the limit. As n approaches infinity, this is approaching 0. So is this. So is that. Okay, so hopefully you see that the limit is 0. The limit of this is 0, and then 2 times 0, that is just 0. So we conducted the ratio test. And we got the result is less than 0. Well, that tells you that this series, this initial series, converges absolutely. All right, so it converges. And if anything that converges absolutely, well, that converges. All right, so over n squared, and this is raised to the p power. All right, so they want the question here is for what values of p does the series, you only have 1 minute left, for what values of p does the series converge? Well, what I'd like you to be able to see here is you could rewrite this n as 1 to infinity of 1 over n to the 2p power. I'd like you to be able to see that's a p series. And for this to converge, one of the things that we said earlier is that this exponent has to be greater than 1. So what you'd have to do here is see that 2p would have to be greater than 1 for this to converge. You divide by 2 on both sides, and p would have to be more than half. Final answer.